In this video, we will learn about making a project in Atmel Studio for a custom board. There are many development boards available, with the environment able to be set up to use them, but starting with a custom board can be more tricky. For my example, I will use a SAM4S8B ARM microcontroller. I have made my own board using this chip and now want to make a program for it. My program will have the microcontroller waiting for a button press, at which point it will blink an LED and send a command to a peripheral device using the UART communication protocol. My peripheral device is a Wi-Fi module, so this example may illustrate making a doorbell that sends an email to you whenever the doorbell is rung. The first thing we will do is open Atmel Studio, and this is the screen that you will see. Next, we will click on New Project to start a new project, and we'll select the ASF board project here and name it something. You'll also pick where to save it to, and then when you're ready, hit OK. And it's going to load the boards and ask you which board you have or which microcontroller you have. And so here I'm going to select by device because I don't have one of the pre-made boards, I have my own board. And I know that I am in the SAM4S category, and I have the SAM4S8B chip right here, so that's what I'm going to select and hit OK. And that's going to open up a blank project. And this is the screen that you will first see. So just to look at the structure a little bit, there are a couple of files I want to point out. If we open up the source right here, we can see there's a main.c file, and so we click on this and it's pretty much just a very simple template with only one function that's actually defined right here inside the main, which is the board init function. And if we also click on the config right here, we see there's a conf board file where we're going to configure our board, and right now it's empty. And also we can see what this board init is going to do, and in general this is a good thing to do in Atmel Studio to find out what things are doing, is we can right click on it and say go to implementation, and it'll ask you where, and so we're going to go to the init.c function over here, and that shows us what this is going to execute. And right now, again, this function is empty. Now, if we were to select a development board, such as the Explained Pro from Atmel, all of these would be filled with things corresponding to that board. So this would have initializations corresponding to various modules that are already on the board, such as buttons and LEDs and other things that can be used with the board. But since we're starting a brand new project with our own board, all of these things are going to be empty. Another very important part in Atmel Studio that's going to be very useful for us is going to be the ASF wizard. The ASF is the Atmel software framework, which is going to make our life a lot easier by allowing us to manipulate the registers in a microcontroller not directly, but through drivers and services and functions, which will allow us to do it without having to actually look at the datasheet at every single register that we want to change for every single function. So to access that, we can go to the ASF wizard, which was the first thing that opened up when we started a new project actually, or we can click on this right here, which also would take us to the ASF wizard, and we have to select the project we're going to be doing this for. Since we can have multiple projects in one solution file, we'll click on our tutorial project, and that opens up all of the modules that we currently have on our board. And right now all we have is the generic board support driver right here, but we can select more. And so a couple ones that I am always going to use is going to be the system clock control, and you click it on the left and you say add, and also delay routines to create delays, and I'm going to say add, and when I'm ready I say apply, and now these are going to be added to my project. And so if I actually click on source now and look at the config file, one more has been added for the conf clock to configure the clock. And if I click on that, I can see it has a bunch of definitions for what the clock is going to be. Now going back to the ASF wizard, since I said that this is going to have a button and it's going to use UART, I also know a couple more modules that I want to add to this. Now, I don't necessarily know them before I ever started using this, but after using this for a while, I got the hang of it and I learned which ones I need. And so I'll show you how I know them a little bit later on, but for now, I'm just going to add the IO port service, the GPIO service, and also the USART. So the S here is for synchronous, since this is a universal synchronous or asynchronous receiver and transmitter. So it just packs a little more functionality than just a simple UART. But we're not actually going to use the synchronous part, but this is the service that we're going to use. So I'll add that too and hit apply. And now all of these things are available to us. And once more, we get one more configuration file, config UART serial, but I'm not going to actually use that. Okay, so the first thing I want to do here is to change my clock configuration, or not really change it, but just look at it a little bit and just explain a couple of the parts. So all this does is it sets things up in order for us to be able to configure the clocks that are going to be used in our system. And what this is currently saying, this is the default right here, I haven't done anything yet, is that we are going to use PLLA, that's right here, the PLLA clock, which is going to be from our PLL, which can multiply our input clock. And you can see there's a bunch of different options here to use. We can use the internal RC oscillator for the main clock, which it can be at 12 megahertz. We can use a crystal, which is what I will be doing, and the crystal can be multiplied using the PLL. And there's a lot of options for our system clock source. And then we can also configure a prescaler here, and so by default it's set to a prescaler of 2. That means whatever we have coming in will be divided by 2. And furthermore, the source here, the PLL, will multiply our input, which for me is the crystal, by 20. And so altogether we're going to get 20 times divided by 2 because of the 2 times prescaler, and my input crystal is 12 megahertz, so this will result in 120 megahertz for my main system clock. Now for the second PLL, I'm actually not using this, so I don't want to activate it, and I'm going to comment all of these things out. Also the USB clock, I'm not going to use that, so I'll comment those out, and all I'm left with is my main clock source here from the PLLA. Now I'm ready to actually make my program. And so all of this stuff right here, if you want to include documentation, it tells you what to do here. And I'm actually, just for simplicity, I'm going to erase all of this just to keep this more plain. And notice it says insert system clock initialization code here. And so there's a function that you will see in pretty much every sample project that is sysclock init, and that will initialize the system clock. And then we also have our board in it, although we don't have anything there yet. And then it says insert application code here. So in general, the way these things are going to go is you're going to have in the main loop, you're going to have, or in the main function, you'll have some initialization code, and then you'll have an infinite loop, so while 1, that's just going to keep on running. And in here, we're going to do what I said. So we're going to just make comments for this for the moment. So I'm going to say that we're going to detect button level, and then if high, then we're going to light up an LED just to show it and send a message over the Wi-Fi chip that I mentioned, or over UART. If low, turn off LED. Alright, so these are just placeholders for now. So what's going to happen is the board's going to initialize, and then it's going to just do this over and over, waiting for the button to be pressed and lighting up the LED and sending a message accordingly. So how do we actually do these without having any kind of point of reference? And the answer is we're going to use sample projects, example projects in Atmel Studio, which are going to illustrate the various functionalities that are available to us. So for this, I like to open up another instance of Atmel Studio, just not to crowd this one. And so here I'll pull this up, and I say new example project. And so it's going to take me to this window. And once more, I'm going to select the SAM4S device family, and we can see here that there are a lot of sample projects for us to choose from. And also, one thing to point out here is this number over here. This is the version of the ASF, and so I want to use the newest one at the moment. That's 3.33.0. And so right now I want to find how to use the button. And buttons are used in a lot of examples actually, but if you try just searching the word button, you're not going to find anything, unfortunately. But I know that this is going to use my input-output port, so I/O port, so I'm actually going to look for an I/O port program. And so here we go. We have common I/O port service, and I'm just going to choose this one right here. All of these boards that it says, these are boards that it uses for the example. They all use the SAM4S family, although a different version of the chip than I'm using, but that's okay. So I'm going to hit OK, and it's going to ask me to agree to this license, and I say finish, and it's going to load up the project. And here we go. So I click on source, I open up the function here, and here it tells me a little bit about it. This example demonstrates how to use the common I/O port service for pin input and output. And so this example reads input from a button and outputs it on an LED, so that's perfect for what we're doing. And so the thing to do here then is to explore this solution and really see what's going on. And so again, they have this main function with the sysclock initialization, the board initialization, and by the way, if I click on this board initialization and go to it, it's a lot more complicated than what we're going to have, because this defines all of the various things that can possibly be implemented on this development board. So ours is going to be much simpler. And then they have I/O port init, that's to initialize the use of the I/O port service. And then you kind of get a hang of it by looking at these. It says I/O port set pin direction of the example LED to be an output. You set the direction of the button to be an input. You set its mode to have a pull-up on it, so that is by default going to be high. And then this infinite loop that basically says we're going to set the pin level of the LED to whatever we read from the button. Right? We're using the I/O port get pin level of the button. Alright, so there's a lot of things here that are potentially undefined for us. What does example LED mean? All these things that are in purple are predefined somehow. And so some of these are actually predefined by the system and some are predefined by us. So I/O port dir output is something that's predefined, and if I go to its implementation, I'm taken to the ioport.h file, which is not something that we created. That was something that we got by including I/O port service in the ASF, and we can see that it's just this definition here that's going to be used by the system to indicate that this is going to be an output as opposed to an input. But if we click on the example LED, that takes us to something that was actually defined in this conf example file, and it was defined as the pin PWM LED0 GPIO, and again, that's not something clear either, so we go to that implementation, and that takes us to this definitions file for this board that we have, and it says that it is pin PA19, and so this is the ID pertaining to that pin. Again, we can further click on this, and it takes us to actually definitions of these various chips, and so that tells us that this is going to be ID 19 if we click that far into it. But really all we cared about was this part right here, because that's what we're going to copy into our program. And so we see that that's how we can define a given pin and then use it, and that's exactly what's done over here. The same kind of thing is done for the example button. If I click on that, again, I go all the way through, and I see that it's going to be PB3. That's the pin that we're going to use for the button. So for us, that may be something different, but this is the style that we're going to use. And so now for my own project, I'm going to go to my conf board file, and I'm going to add those two definitions. I'm going to say #define, and I'll call it pin button. And we'll make that, for me, I'll make it pin PA23. IDX as was done in the example, and also I'm going to have an LED pin which is going to be A20 IDX. Okay, so now I have these definitions here, and I want to also initialize them to some values. And so for that, I'm going to go to that init file. I'm going to find it by going to this board init, saying go to implementation, and it's going to take me to that init file. And right now it's empty. But now I'm going to include those initializations that were made in the sample program. Specifically, I'll include IO port init to initialize the IO port. And I know they did this in their main function, but I just want to keep this a bit more modular, keeping all my initializations here. And I'll say IO port set pin direction of my LED pin, and once you actually write a valid value, it's going to highlight it in purple or change the color to purple, and I want this to be an output. So I'm going to type in that, close that out, and further I want to set its initial level. I want to initialize the LED to be off. So I'll say pin LED. By the way, when it has this autocomplete, you can hit enter and it's going to complete it with whatever was highlighted. And I want to initialize it to false, so it's going to be off. And for my button, so I can also autocomplete like that, IO port set pin direction. The button, I want to be an input. And I also want to make it not a pull-up as it was in the example, but I actually want it to be a pull-down, so that by default it's going to be low, and when I click the button it goes high and the LED will light up accordingly and will send a message. So these are my initializations that I want for my system. So now I can go to my main function and actually change a couple of things here. So I can say if, and this is still based on that sample project, if IO port get pin level of the pin button, so that's going to tell me what that level is. If that returns true, if it's high, then I'm going to say IO port set pin level of my LED to be true. And then for here I'll still put a little placeholder. I'll say let's send the UART command, and then I want to also include a delay. So delay underscore ms. You can also find this in various projects and various sample projects, but that's a very common one that I use all the time, to delay for a set number of milliseconds. And I'll delay for 500 milliseconds so that if the user is holding this down, we're not constantly sending commands. We send them only once every half second. Okay, so we have this delay, and then we also should have an else statement that says that if the button is low, we're going to set the pin level of the LED to be false, to be off. Now we want to send a UART command. So for this, we're again going to open up a sample project. And I'll go to the same exact sample project that I had before, and I'm going to say File, New, Example Project. And once again, I'll select the SAM4S family. And here I'm going to search for USART examples. And I'll just choose a serial example here, this one. And here I've also selected to add it to the solution instead of creating a new one, so it'll just add it to that, so I have them all side by side. And once I hit finish, it creates that project for me, and it's available right here. And so I can click through to its source and take a look at it. Now this project is going to be a bit more complicated and use things that we're actually not going to use, so we're going to have to pick and choose. So if I actually look through this, there's a lot of stuff going on. They try to pack everything into one function, into this one main function, instead of splitting it up among many. And I prefer to split it up and keep it modular, but this is just to make it self-contained. So they have the initializations for the USART and also for other things, and configuring the USB console, and all sorts of things. And then we finally scroll through here and we get to the main function, which itself also includes a lot of various things, because this also displays things through the USB if you want to debug your program more easily. But notice again some similarities. It has a sys clock in it, it has the board in it. It also has some other configurations, but the one we care about is to configure the USART. And so what I would recommend in general when you're looking at example programs, scroll through to the main function and just go through it line by line looking for things that you need. Once you find something you need, go to its implementation and see exactly what it does. So we can see here that this is what the configuration of the USART is going to do. And so I'm going to copy this over to my program, but again, I want to keep things more modular. So what I'm going to do, I'm going to go back to my program and I'm going to right click on source and say add new item, and I'm going to add a .c file which I will call my Wi-Fi interface.c, and I'm going to add a .h file, an include file, also called Wi-Fi interface.h, and it's going to create these two files for me, just templates, and I'm going to fill these in. And so the initialization is going to go in the Wi-Fi interface.c file, and so I'll go back to that example that we have here, and I'm just going to copy the whole thing. I don't need the static because of the way that I'm defining things. So I'm going to go to my tutorial here, and in Wi-Fi interface.c, I'm just going to copy the whole thing, and I'll just change it a little bit. I'll call it configure Wi-Fi instead of configure USART, but it doesn't really matter. And I need to also create a prototype for this in the .h file, so I'll just copy that to here, put a semicolon after it, so that's a function that I can now use in the .c file. Also, don't forget to include your .h files. Now you can see that there are a lot of things that are underlined in red which do not exist in our project. And so the thing that I like to do is first to copy it over to my program here, and then to see what's underlined, and then go back to the sample project and see what those things are. So this was one thing that was underlined, so I'm going to go to its implementation, and here we see that this was actually configured a bunch of characteristics of the USART that we're going to be using. And so I'm going to copy all of these things over because I'm going to need them into my .h file. And this tells you that we're going to be using USART 1. And so just to illustrate, let's say I want to use USART 0 for this. So I'll say USART 0, USART 0. There's a lot of things, and you don't necessarily, when you're starting out, you don't necessarily have to understand what all these various things mean, the ID versus this over here versus other things here. All I do is just go with a template and just change things appropriately. And this is the baud rate that we want, and let's say that I want to keep it as is. So now I go back to my interface here, and let's see if things became better. They did. This is now defined. We go to the next thing. Well, this actually is only if we're using the SAM4L architecture, which we're not. So I can actually get rid of this whole thing altogether. And this should be on one line. Okay, so that's good. And then we're missing this all interrupt mask. So I go back to my example, and I see that this all interrupt mask is this right here. So I'm going to take that. Again, you don't necessarily have to understand exactly what these things are doing when you're starting out. It's a good idea to understand them eventually when you delve into it, but when you're starting out, it's okay to just copy them over as is. And so now everything is good in this function, and it should work. So now I can go back to my main and include my configure Wi-Fi function in order to initialize my USART and to be able to use that. And so now the commands that I want to send here, I'll also make a function to send a series of commands, and instead of just typing them all out here, once again, for the sake of modularity, I'm going to instead make a function that's going to be called send messages. And so it doesn't yet exist, but we're going to create it. And so for that, once again, I go here and I'm going to make a prototype of this. It'll be just a void return, send messages, also with no arguments. And here I'll define it. And what it's going to do is I wanted to print 3 commands to my Wi-Fi module, which is going to connect to the network. Then it's going to initialize to send an email, and then it's going to actually say the text of the email, which is doorbell rung. But how do I actually write a line to my USART? If I go back to my example project that I was looking at here, and I go to its main function once more, this is actually a lot more complicated than anything that we're doing. This uses the PDC for data transfer, and it doesn't really do anything very directly. And we don't even if you search to this, you're not going to find too many places where it actually uses the USART directly. And it's kind of hard to find a project which does, in fact. And so in this case, you might have to delve a little bit deeper. For this, I would go to the ASF Explorer, and I would go to my serial example here, which opens up all of our modules that we have, and I want to look at the USART, and I want to look at its documentation. So when I click that, it'll open up this documentation here, which shows us all the various functions that are available through this module. And so this is one of those things where you will have to kind of search through, and you'll find that there is a USART write and USART write line. And so this is what I actually want. Again, this is through some experience, this is what you're going to find. You want USART write line, which will take a instance of our USART, which we're going to provide, and then a string that we actually want to write. And so that's what we're going to use. We go back to our project, and we're going to say USART write line. It lights up in red because it's a valid function. And we defined our board USART above as the USART that we want to use. And what we're going to say the message will be, and this is not a real command, but just to illustrate, connect to the network. That's the first thing we're going to do. Then we'll delay by 100 milliseconds. Then we're going to write another line, which is going to say send email. So that'll be my initialization to send the email. Once again, we'll delay by 100 milliseconds. And we're going to finally write doorbell rung. So this is what my send messages command is going to do every time the user presses the button. Now there's a couple of things that are still missing here. Specifically, if I want to use my Atmel software framework in any of the functions that I create, I have to actually do that explicitly. So in every function that you write, include the asf.h, otherwise you're going to get a lot of unexplained errors. It would say that all these functions here are undefined. They use the USART or the clock or anything, and they were defined, but since you don't include it, it's not going to be used. And finally, in the main function, you should also include your own function that you just wrote, so you'll have to include the Wi-Fi interface.h file. And so now, just to verify that everything is going to work, I'm going to build my solution. And here we go. There are a lot of warnings, and these are just various things that I didn't define that have defaults as well, and I don't want to complicate this tutorial. But there are no errors, so this should compile, and it will work once you actually load it onto your microcontroller. So altogether, we have seen how to create a custom project in Atmel Studio. We have seen how to configure a custom board and how to put together a project by exploring example projects and sometimes delving deeper by exploring the ASF component API. This is a simple project and can be expanded upon, for example by using interrupts for the button and sleep modes for the MCU, so that everything is much lower power. However, this should be a good starting point.